Today we're going to discuss forced convection. So let's consider a model problem. So I'm going to have a hot sphere. It's going to have diameter d, and it's going to be held at a constant temperature T hot, so T sub h. I'm going to immerse that sphere in a colder fluid. So the cold fluid is going to be at temperature T infinity. And there's going to be a velocity u naught, which is flowing at the fluid. And the fluid's going to have properties: density, viscosity, thermal conductivity, and specific heat, which we know. What is the rate of heat transfer from the solid to the fluid? Now, in the previous section, we derived conservation of mass, momentum, and energy for an incompressible flow. So in principle, we could use those equations to solve the problem. But these equations are complicated, and they're difficult to solve. I could solve them using software, but that would only work for low flow rates, as we've seen in some of the previous section where we just want to calculate the flow, let alone the energy flow around this object. Solving these equations is complicated. However, we can use the equations to give us a lot of insight. So we can use these equations to sort of drive a dimensional analysis to tell us the important parameters in the problem. And that's exactly how we're going to proceed. So let's solve the same problem two ways. So first of all, I'm going to take our existing equations and make them dimensionless. So what that means is I'm going to define a bunch of dimensionless variables. So I'm going to use the twiddle notation to denote a dimensionless variable. So, for example, I could take our coordinate direction and I could divide it by the only length scale in the problem, d, and I could measure length in units of diameters of the sphere. So my coordinates x, y, and z, I could just sort of divide my length in meters by the diameter and measure all my distances in units of how many diameters away from the sphere I am. And now it's important to realize when we do this that this changes our differential operators. So embedded in our equation are lots of things like the partial derivative of something with respect to x. So if we make the partial derivative dimensionless, because this has units of 1 over length, we simply change the units. So I'd say partial with respect to. So everywhere I have a derivative with respect to x, all I have to do is divide by 1 over d, and then I can take my derivative in my dimensionless units. And so what that means is any derivative in x, y, or z is going to have this following form, which means when we have things like the gradient operator in our equation, that's simply going to convert in dimensionless form to picking up a factor of d out front. And this isn't that interesting, right? This is just simply a change of units. If I'm going to measure my gradients in terms of meters or millimeters, I would expect to have a factor of 1,000 converting between those two units, right? So a temperature gradient of some number of degrees per meter is going to be much greater than the number of degrees per millimeter. So this is what the factor of 1 over d is, to simply change our units. So all my derivative operators will look like that. Something like the Laplacian, second derivative, simply picks up a factor of 1 over d squared by the same. So my dimensionless Laplacian will have factors of 1 over d squared. Our velocities, we only have one velocity in the problem, which is the velocity of the mean flow. So we can convert that to being dimensionless by the following. So my velocity twiddle vector will be nothing more than the velocity measured in meters per second divided by the velocity of the flow. We also have time, shows up in our equations. Time twiddle have to be divided by some t naught, some time. Now it's not really clear exactly what we should use, but there's only kind of one time that naturally shows up in the problem, which is if we think about our sphere here with diameter d and a velocity u naught, the time it takes fluid to sort of traverse around this sphere is on the order of d divided by u naught. So the distance divided by the speed gives us the time it takes to traverse, so that's as good as anything. We also have pressure showing up in our equations. It's not really clear what we should use for that, so I'm going to leave that arbitrary for now. So my dimensionless pressure will be some pressure divided by P naught. And then finally is the temperature. Now if we think back to when we did the same type of thing in conduction, we defined our dimensionless temperature first by taking a difference. So in this case, T infinity is as good as any temperature to take the difference from. The far field fluid temperature, how hot are we above the far field? And then we would divide it by the only temperature difference that we have in town, which is the temperature of the sphere minus T infinity. So this is nice because it's bounded between 0 and 1, right? Because when the temperature, when we're near the sphere and our fluid reaches the temperature of the sphere, we would have at most a temperature in dimensionless terms of 1. And when we're far away from the sphere out here, we would approach T infinity, and so we'd have 0. So now we just have to take these substitutions and put them into our equation. So we just need to substitute all of these into our equations. Okay, let's start with the momentum equation. So we want to have the partial derivative of v with respect to t. We want that to be a dimensionless term, so that means I'm going to pull out my factor of u naught and my factor of t naught. And then I need to add that to my v dot gradient v. And these are all dimensionless. And so again, when we want to convert to dimensionless, I need to pull out two factors of u naught because I have v and v. So I have a u naught squared. And I need to pull out a factor of 1 over d because I've got the gradient in here. And so this is my material derivative of the velocity, or the acceleration, which needs to be multiplied by the density. So that's the left-hand side of our momentum equation in dimensionless terms. Now I have minus the dimensionless gradient of the dimensionless pressure. So I need to pull out a factor of P naught and D. Finally, I have the dimensionless Laplacian of the dimensionless velocity, which means I need to pull out a factor of U naught and D squared. And remember, while this might seem a little bit confusing or a little bit arbitrary, all we're doing is simply changing units from ones measured in meters and seconds, which are sort of arbitrary units by man, to ones that are sort of natural for the problem. So using the velocity and the length scale natural to the problem. Now if I look over here, I notice I can rearrange this term as simply u naught squared over d. So I have a u naught squared over d. So I can factor that piece out. And then by convention, what I'd normally do would be to sort of multiply this term and move it over to this side. And now it gets a little annoying after a while when you do this to carry the twiddles around. So I'm going to drop the twiddles and just use red to denote dimensionless variables. So my dimensionless acceleration, dv dt, is going to equal to p naught rho u naught squared minus gradient p. Hold on, I forgot viscosity. It's like that term looks wrong. So I need the viscosity, multiply the d over here, that cancels and leaves me 1d on the bottom. U squared on the bottom leaves me 1u on the bottom in 1 rho. Now my p naught I left as arbitrary, so at this point you see that a good choice for p naught would be by definition to set it to rho u squared, which will make the factor in here become 1. And so now my equation in dimensionless terms is quite nice, where we should recognize the only parameter that's left as 1 over the Reynolds number. So this is completely consistent with everything we've already done in this course. So we've already actually done this part of the problem before. So we have 1 over the Reynolds number is the only parameter that shows up in the momentum equation. Our other expression is conservation of mass, which says the velocity has no divergence. So if we convert that to dimensionless terms, we would pick up a factor of u naught for making the velocity dimensionless, and a factor of 1 over d for making the divergence operator dimensionless, and that's equal to 0. And this is quite convenient since this side is 0. I can just multiply by that and nothing happens. And so my conservation of mass is just the dimensionless velocity also has to be divergence free. So conservation of mass and momentum, I have one parameter in the problem, which is the Reynolds number. Now let's do energy. Now recall that we defined our dimensionless temperature as both the difference and the dividing by the difference between the hot object and the cold fluid. So what this means is when we convert to units, I have to make the following substitution everywhere I have t in the equation. And the only important thing to realize is that this t naught is going to disappear because everywhere in our equations we have things that look like the derivative of temperature, either with respect to time or space. And when I take the derivative of this, my constant difference, t hot minus t infinity, can be factored out front, but the derivative of a constant with respect to time or space is always going to be 0. So I can always basically get rid of that constant. So our equations then, conservation of energy, I have a partial derivative of temperature with respect to time, which means I need to factor the t hot minus t infinity. To make temperature dimensionless, to make time dimensionless, I need my d divided by u naught And then I have to remember this whole term over here is going to be multiplied by rho Cp. And let's just put twiddles over everything to be clear that the red is, again, our dimensionless variables. When I make the term v dot gradient temperature dimensionless, I pick up a factor of u naught for the velocity. I didn't leave myself enough room, but the T hot minus T infinity for the temperature, and a 1 over d for the diameter, which comes out in the gradient operator. And that's going to equal the conductivity times the second derivative of the temperature, which means I'm going to pick up again a factor of T hot minus T infinity divided by d squared. And the viscous dissipation we're just going to ignore. So again, we can, just like we did in the previous one, we can factor these things out. We'll notice that every term has a T hot minus T infinity, so I can eliminate that. I'll notice I've got u naught over d, u naught over d, so I can simply factor that out front. And then just like before, I can move these terms to this side of the equation. And for convenience, I'm going to drop the twiddles and just use red to denote dimensionless variables. So I have d temperature, d time, but material derivative of the temperature equals, and now I'm going to have K and so now we can rearrange this a little bit. So if I look at this parameter here, K over rho Cp we know is equal to the thermal diffusivity, the fluid, right? If we remember from conduction, K over rho Cp was the diffusivity, which has units of length squared over time. So I can rewrite this as alpha over du naught times the second derivative of the temperature. But if I also remember the diffusivity of momentum, or the kinematic viscosity, is defined as u mu over rho, I can do what seems at first like kind of an arbitrary substitution, but it'll get us somewhere, which is I can multiply the top and the bottom by that. And then if you notice, this parameter here is 1 over the Reynolds number, so d u naught over the kinematic viscosity. And what I'm left with is a new parameter, which is the ratio of the diffusivity of heat to momentum. What's called the Prandtl number is usually the inverse of that. So this over alpha is called the Prandtl number, and it's a property of the fluid, and it's a dimensionless number. So written in terms of the Reynolds number and the Prandtl number, our final equation is as follows. So the temperature field depends upon both the Reynolds number and this new dimensionless number, the Prandtl number. So the Prandtl number we usually abbreviate as PR. For a fluid like air, the Prandtl number turns out to be something around 0.7. For water, it turns out to be somewhere around 7, liquid water. For a fluid like oil, it turns out to be a big number. For a fluid like a liquid metal, it turns out to be a small number. And the reason is because the Prandtl number is the ratio of the diffusivity of momentum to heat. So a fluid like oil is very viscous, but it doesn't dissipate heat so easily, so it's a big, big number. And a fluid like a liquid metal flows nicely, but it has a very high conductivity, or it has a very high diffusivity of heat. So it turns out to be a low number because this number is bigger than that. For a fluid like air, the diffusivity of heat and momentum are comparable, so the Prandtl number is pretty close to 1. But we still haven't addressed the question of what's the total heat transfer from our sphere to the fluid. So previously, we empirically said that we would describe heat transfer from a solid to a fluid. So the heat flux dotted with the normal vector, evaluated at a point on this surface, we said was equal to some constant h, which we call the convection coefficient, times the temperature of the solid, which is T hot in this case, minus the temperature of the far sphere fluid. And previously, when we did problems of conduction, where we talked about heat in the solid and we want to talk about a boundary condition with the fluid, this h parameter was a given. Now we actually want to calculate it. So if we take our microscope out, and we go in and we zoom here at the surface, we have some boundary layer that develops around there, right? So we have the fluid sticks to the surface, so there's no velocity. And then it progresses away. And this solid is hot and the fluid is colder. So the only way right at the surface that there can be any heat flux is by conduction in the fluid. So right here at the surface, Q dot N, the flux that's passing right through that boundary, is equal to the conductivity of the fluid times the temperature gradient in the fluid right there at the surface, dotted with the normal vector. So this quantity Q dot N is given by conduction in the fluid, because at the surface there's no flow, so there's no carrying of the heat away by the motion of the fluid right at the surface. So now let's convert this quantity to our dimensionless form. So we have the conductivity of the fluid, and the normal vector already has no unit, so I've got the dimensionless gradient of the dimensionless temperature dotted with the normal vector. So just as on the previous page, we had, when we make the temperature dimensionless, we pick up this factor of the temperature difference divided by D. Let's not forget our negative sign. And we're going to say this is equal to H times T hot minus T infinity. So that means that factor of T hot minus T infinity cancels. So the dimensionless temperature gradient turns out to be equal to HD over K of the fluid, which ends up looking an awful lot like the BO number, if you remember from our study of conduction. But remember we talked about the K and the BO number was the conductivity of the solid. Here the conductivity is the conductivity of the fluid, so this is not the BO number. Instead it's something we call the Nusselt number, so it's a new dimensionless number. So it's HD over K of the fluid. The other important thing to realize is that the heat transfer coefficient H is a local quantity, but usually in practice we often just have an average quantity, so we don't really care about the details often. Not always, sometimes we care about the details, but many times we just want the average heat transfer coefficient for the object, so the total amount of heat from the solid. There we would say the total heat transfer is equal to H bar, the average heat transfer coefficient times the area times the temperature difference. So we can talk about a Nusselt number being a local quantity with a local value of H, or an average quantity with an average value of H. So now let's talk about the real magic of all this stuff that we've done. What we've shown then is that the average Nusselt number, so NU bar, is a function only of the Reynolds number and the Prandtl number. And remember, the Reynolds number depends upon the velocity and the size of the system as well as the fluid properties. The Prandtl number is just a function of the fluid properties. So this is very similar to what we did when we talked about drag. There we had drag being a function of only the Reynolds number, so we were able to plot drag coefficients on a single dimensionless curve. Here we can plot a family of curves. So we might have something like the following if we plotted on the log coordinates, so maybe log of the Reynolds number versus log of the Nusselt number. And we measured the Nusselt number for different Reynolds numbers. We might find the data mostly fits along kind of a straight line. And if we repeated for different fluids with different Prandtl numbers, we might find a family of curves. So it's very common then in cases just like in drag where it's difficult to predict the details, especially when the Reynolds number is large, to sort of fit data. So a very common functional form you'll see is that the average Nusselt number is some constant times the Reynolds number to some power times the Prandtl number to some power. And a very common number you'll see for this power is 1/3. So if you look in a heat transfer book, you'll find a number of correlations for Nusselt number as a function of Reynolds number and Prandtl number. So here's an example. This is from a textbook which still is in print by maybe different authors, but Fundamentals of Heat and Mass Transfer by Inker, Pereira, and DeWitt. This is my old edition from when I was an undergraduate. And if you look through it, and there are sections on convection heat transfer, you'll find a number of things. Here's one example. This is for flow over a cylinder, so similar to the example we talked about. And here they're showing the local Nusselt number. So this is as a function of angular coordinates as you move around the circumference of the cylinder. This is the local Nusselt number as a function of this angular coordinate, and they're showing curves for different Reynolds numbers. So this is how the local Nusselt number changes as you move around the cylinder. And then if you look at the mean Nusselt number, they have some formulas down here where they have a table for different Reynolds numbers, some constant C and some constant M. And here they're saying these are constants for equation 7.55. So if we flip and we look for equation 7.55, it's right here, which is exactly what I had talked about before. So it says some constant Reynolds number to the power M, Prandtl number to the 1/3, and that's the average Nusselt number for the sphere. So the way you would do it is simply, once you know your Reynolds number, you look at this table, get a constant C and M, and then you just simply plug it into that formula, and that allows you to calculate your average Nusselt number. And if you flip through this book or any other book like it, you'll find a number of different correlations. Here are some different constants C and M for the same type of functional form for squares, hexagons, plates, and whatnot. These are all from measurements, so people over many years have done measurements in many geometries and sort of fit their data to different functions. Maybe an interesting to look at here, as this measurement here was done in 1949. So this is stuff that's been around for quite some time. If we flip ahead, we can find correlations for a sphere. So if we had a sphere instead of a cylinder, and again we find it's saying here numerous correlations have been proposed. Whittaker recommends an expression of the form, and here they have this funny thing: 2 plus the Reynolds number to the 1/2, Reynolds number to 2/3, Prandtl to the 1/4. And so this is pretty typical of how this goes, is people take data over a number of years, they fit the data to functions which might be relatively simple or practical to use, so they're not overly complicated, and then they allow you, once you know your Reynolds number and your Prandtl number, to get the average Nusselt number. So we're going to have a cylinder with a diameter of 10 centimeters or 0.1 meters. We're going to immerse it in water, and we're going to flow water over it at 1 meter per second. We'll imagine that we can hold the cylinder hot at a fixed temperature of 350 Kelvin, and our water that flows over it will be at a fixed temperature of 300 Kelvin. Kinematic viscosity of water is about 10 to the minus 6, so our Reynolds number is about 10 to the 5. Prandtl number for water is about 7. So if you recall, our empirical formula has a form, some constant Reynolds to the m, Prandtl to the 1/3. So now let's look in the book. Let's look up the correlation. We look up the values for that Reynolds number, and that tells us our value for C is 0.027 times the Reynolds number to the 0.805 times the Prandtl number to the 1/3. So don't read too much into these numbers. They're just sort of fits to data, so there's nothing magic about the 0.805. That was just the number that kind of best fit the data that these authors took in 1949. And if I plug in my value for the Reynolds number and the Prandtl number, just simply put this into the calculator, I get an average Nusselt number of about 546. So the definition of the Nusselt number is HD over K equaling 546. The thermal conductivity of water I need to look up to sort of convert this to find the average heat transfer coefficient. So it's going to be 546 times K over D. Turns out the thermal conductivity of water is about 0.6 watts per meter Kelvin. So if I plug in that value for K, that value for D, I get H bar is equal to 3280 watts per square meter Kelvin. And you always have to remember that these heat transfer calculations, when you're using these empirical fits, are not good to any real high degree of precision, so calling this 3280 is probably overkill. Normally I would just say H bar is about 3000 watts per meter Kelvin. So anyway, that's just sort of a quick example to show you how you can use these kind of correlations in dimensional analysis to get the answer. And again, the magic comes from not any of these particular numbers here, but that by analyzing our equations, we get the average Nusselt number is a function of only 2 dimensionless parameters. So it allows us, just like we've seen before, to do a limited number of experiments to be able to explain a wider range of physical or dimensional quantities of heat transfer.